Welcome to the second video on Chapter 7. In the first video we addressed the strengthening mechanisms. We want to now know how heating affects these strengthening mechanisms. So I'm going to start off down on the 26th slide of the PowerPoint that I sent you, where you can see there are different ways to go about shaping a metal after you have gone about the process of creating the material. So these are just different examples that are shown here, different titles of different ways to basically reform your metal. Now, the rolling here is what we've been referring to when we say cold rolled steel. If you at room temperature roll this steel, or at least a warm temperature and not a very hot temperature, if you roll this steel, then you're going to see an effect called strain hardening, which is really important to changing the properties of the material that we've been studying so far using our stress strain diagrams. So the dislocations or the defects, the linear defects that we've been looking at, are actually changing as something is drawn or cold worked. When something is cold worked, you can see that there's an action that occurs on these various fronts. So the yield strength of the material is going to increase because of what we were talking about before, how you get dislocations moving around. And as the dislocations move, that is the process of the material yielding, right? When those dislocations no longer are able to move anymore because they get locked into place, then the strength at which that material yields increases. Now, you have seen this in a diagram before where we watched the stress strain go up like this, and we said that if we release the material at that point, it would come back along this line and then go back again. So you can see in this way that the material's yield strength at this point is quite different than its yield strength at this point. So it's actually increased the yield strength by that diagram. But internally in the material itself, then you can imagine that if you have, this is I think an example that you can intuitively understand. If you take a knot, take a rope, there are two ropes that are cut and you tie them back together into a single rope using a knot, right? Then if you've got these two ropes and a knot is sort of tied together but not quite tightened, and you yank on the two ropes, then these are going to slide a certain amount until they tighten. So you'll get a lengthening effect, and then those knots will really they'll go through as much sliding as they possibly can until they can't slide anymore, and then the amount of force that you can pull on this is much larger than it was up here where they were not entirely taut. So that's actually a visual for what's happening inside the material, where you've got planes sliding until they can't slide anymore and they catch, and then that increases the strength of the material. So on the yield strength and the tensile strength, you can hopefully see why that increases those. The ductility, on the other hand, the ductility decreases, and the reason is because the ductility is really this process here where you're allowing sliding to occur. Ductility is essentially the ability for planes to slip planes to slide. So if you've locked them all up, then they no longer have the ability to slide. You have then decreased the ductility. Okay. This is just a graph of different cold working on the same material. And so if you cold work the material and then use the stress strain diagram, then here the green is the stress strain diagram for something that has not been cold worked. That same material that had a 4% cold work now has the blue diagram when tested using a tensile stress test. And then the red is now the same material except for it's been 24% cold work. So you can see how these features are affected. Cold working is essentially mathematically defined as essentially it's like reduction in area or percent area reduction. So you take assuming that you have a cylindrical sample here, then we would say take this to be a pi r squared or a d squared over 4 for the cross-sectional area of our sample. So like I said, it's like percent area reduction here. That defines how much work has been done. Remember that the amount of length drawing that's occurred in a material is then proportional to the area reduction by the Poisson ratio. So this is basically a discussion about how much something has been drawn, how much percent elongation has already been used up, right? And so if we wanted to address this in terms of area, we could then, which we do, this is a standard way to talk about how something has been cold worked. Percent cold working then is determined by the initial area minus the final area over the initial area. We're really going to have to look at the advantages of cold working something. You can see here for a piece of copper, after it's been 35.6% cold worked, that's this same piece of copper that was in our previous slide, after it's been drawn out, then we can use the graphs here. So these graphs, this line here represents data that has already been acquired about copper. Also this one, data that has already been acquired about that same type of copper. So then this line, the 300 megapascal line here, that is an anticipation. That is what we would expect to happen if we take our copper and we draw it out this much. We can use these three graphs to determine what we would expect the material properties to be of our cold worked copper. So we can analyze it in the dimension of yield strength and tensile strength and see how those increase. And we can also analyze it in terms of percent elongation. So remember, percent elongation is not, do not confuse that with how much this has lengthened. It's actually more related to how much it has left to go before it begins, before it snaps, right? So percent elongation, then the smaller percent elongation you have, then the less ductility you have. So this is a measure of ductility, and then these are a measure of how hard you can tug on something without it changing or breaking, right? So notice here that our the strength of the material in both tensile terms and in yield terms has increased, but we have lost the ductility. It's become a more brittle material, in other words. So we would check on each of these graphs. You would check 35.6%, 35.6%, 35.6%. See where you land, and they have provided these values for us and said, oh, that means that you landed at 7% elongation at 340 megapascals of tensile strength and 300 megapascals of yield strength. Okay, now reading these graphs is one thing, but being able to make a material to exactly your specifications is an entirely different thing. So what if we overdo it? What if we cold work something so far that we are down to 7% elongation and we're displeased with that result? We do not like something being so rigid, so brittle. Then can we fix it? Yes, we can actually reverse the effect statistically, and the way to do that is to heat it. We also call this annealing. So in order to, annealing is just basically, it's careful heating. So essentially annealing is the term that we use to refer to a strategic process of applying a very exact heat over a very exact interval of time. Now, so they actually, they wrote annealing here, I didn't see that. So if we anneal a sample, then what you can see is there are three phases that this material undergoes, where, and we'll look at the atomic version of that, but there are three phases that this material undergoes. The first one is that, we have a recovery period where essentially the knot unties. So during the process of the knot untying, it's basically getting around barriers that has been locked. So we said that the planes had the ability to slide when something is ductile, and they no longer have the ability to slide when they are not ductile. So the whole idea is that the recovery period is the process of beginning to release those planes from their locked state. Then once they are no longer locked, then more and more of them free up during the increase in ductility phase, which is the recrystallization phase, which is where you begin getting the domains that were locked before are now, they have a tendency to form new domains, new little regions of, you remember when we were talking about domains, we were talking about different little regions of crystal, right? Once those have been locked up, then the recovery starts to release all the boundaries a little bit, and then the recrystallization portion is where it begins to form different domains, and they have a tendency to form small domains at first, and then they begin to, during the grain growth period, they begin to take over like countries, essentially, like tiny countries taking over smaller countries until they get larger grains. Okay, this actually looks a lot like the time graph, except for the time graph would actually increase ductility in this region as well, like so. Okay, so so this is a little bit misleading. We would actually choose one temperature at which we would begin this process, and that temperature is given by this recrystallization temperature. So somewhere between about a third of the melting point of that particular material, and you'll find it somewhere in this region, and about 2/3 the melting temperature. Okay, so you're going to set something at a certain temperature and then let it stay at that temperature until you've recovered it to its previous state. Okay, now let's look at a problem to talk about the best way to go about matching up the specs that someone else has provided for you. If we took a cylindrical sample and we draw it out, like I said before, we on our copper sample, when we decreased it from one initial radius to a final radius, we had reduced its percent elongation to 7%, which is quite low. And the problem then is if we are to try to heat the material to restore it some of the way, it's not easy for us to exactly know whether that heating process is going to work the same every single time. So in other words, we know cold working much better than we know that temperature process. We know how to cold work to an exact specification, but we do not know how to recrystallize very well. You can find that out, you can go through all the science and everything, but really in industry it's not that helpful to go through that process, so it's a little bit inexact with the recrystallization. So what our method is to cold work as we need, and then if we need to reset the material, we could do that for this new piece of copper that we had previously drawn out. We can reset this percent elongation to its original by heating it, right? And then we can cold work it some more, and then we can reset it, and we can cold work it some more, and we can reset it. So what we really want in order to cold work something exactly to spec is to keep resetting it until we're ready to cold work it exactly to the amount that we want. So keep that in mind as we address this new problem. So the new problem is we have a brass rod this time. Here's our rod. So brass rod got a diameter of 10 millimeters, and we want to draw it pull on it, in other words, stretch it until it reaches 7.5 millimeters. That's our new final diameter. Just a little bit smaller, 7.5 millimeters. Now, we have some requirements. What are those requirements? This states that the tensile strength needs to be greater than 380 megapascals, okay, or 55 kilo psi, or kips. We also require that the ductility has to be greater than percent elongation of 15%. Okay. Okay, so now how are we going to go about this process? Now remember, what I suggested before is our process is generally we want to cold work this a little way to some intermediate diameter, okay, and then we reset it and cold work it the rest of the way to the 7.5 millimeter diameter, okay. That way we can very exactly choose our specifications at this 7.5 millimeter diameter. So what we're going to have to do in this problem is work backward. We're going to work backward to say, I would like to know what this value is. In other words, if I were to look for the material's exact specifications of more than 15% and higher than 380 megapascals, then what radius would I want to start with if I were to get to 7.5 millimeters? And then what we can do is we can work it down to that radius and then reheat it, right? So let's find that out. We need to look at some charts in order to know what that is going to be. So first, like I said, if we were to, so this is kind of an erroneous way of going about it. If we were to directly draw it to the final diameter, then we would reach 43.8% cold working, right? It is not a good strategy. That's a lot of cold working, so you're probably destroying the thing in the process. Okay, so now let's look at, so this is not a good strategy, right? This is a better strategy. Here's why. Well, let's look at these diagrams and this is actually diagram 7.19 in your book, so you can use this for these three materials: copper, brass, steel. Notice that the copper graph is the same graph that we saw in a previous slide, but now we've added 1040 steel and brass. Now we look at our brass curve, and we can actually use this curve to say, oops, this is supposed to say yield strength. We can use this curve to say, okay, we're interested in the tensile strength here, and we're interested in the percent elongation. So this one is just a bonus. Over here, the yield strength is a bonus. These are the two that we have to monitor. We're interested in something that has a higher than 380 megapascal tensile strength, okay? And we're relevant to this brass curve here, right? That's the one we're interested in. So we'll definitely need it to be greater than 12% or so, somewhere around 12-13%, something like that. If we don't go higher than 12% cold working, it won't be strong enough. If we directly cold worked it all the way to 7.5 millimeter, then we would certainly have enough strength in the material, because 540 megapascals is a very high tensile strength. But the consequence, as you know, is that we sacrifice the ductility. So we would have gone all the way down to 6% ductility. That is not acceptable. This criterion is not satisfied, right? So what we have to do is say, look, we need it to be greater than 15% ductility. Here's 0, here's 10, here's 20. So we'll take that line right there. And we know that any region in here, any cold working above 12% is acceptable for strengthening. And any cold working, here's where we cross our graph at, what is that, like 20, a little more than 25, 20, maybe 27 or 28, something like that percent. Anything less than that value of cold working will provide the ductility that we need. So that puts us in a range somewhere between 12 and, or whatever this is. I think they give you some exact numbers on the next slide. So let's go ahead and use their exact numbers. Here they have, 12, that's good, and 27. Okay, so 12% and 27. So that tells us then that the range we're looking in, and I'm going to use this graph over here to highlight here what the region is that we're interested in, anywhere from 12 to 27. That's reasonable, isn't it? Let's just now, for the physicists among us, we have a tendency to maximize this using functions, but that's quite difficult when you're dealing with data like this. I think the engineering approach is to say, hey, 20% is pretty closely in between 12 and 27, so let's aim for 20%. So we would say, well, 20% is, it satisfies, hey, if I land at 20%, then what do I get out of that? I get 20% lead on this graph leads to about 400 megapascals. That's pretty successful. That's above 380. And then 20% on this graph leads to 20 to 23, 20, probably about 22% ductility, which is above 15. So that will work, right, around 20%. Okay, so if we want to go to 20%, use 20% cold working. Now I'd like you to remember, I'm going to take you back to our original slide where we, not our original slide, but our original strategy slide. We're saying that we need our final product to be 20% cold worked. This needs to be 20% cold worked. We found that out by looking at the graphs, right? Let me write that as from charts from our charts and our graphs, we were able to determine that this final cold working needs to be 20%. So whatever happens before that, not so worried about, right? All that is just shrinking it down to this very specific size, so that we can then go from that size and cold work at exactly 20% to the final diameter, because we can always just reheat this and then restore it to its original material properties and then send it back, along the path of cold working and strengthening. What this means is that we're concentrating on just these two for now. We need to run a calculation to determine what that question mark there is. So we're going through that process here, and we're saying, well, the percent cold work here, I want it to be 20%, right? So if this is 20%, or and that's 100 there, so this is 20. Or later on you can see that they fill it with 20, right? But so if you were to fill this in right now, you would see that this equation is given as 20 is equal to the original diameter minus the final diameter, but that's the same as the original diameter over the original diameter, right, squared, which is just 1. So 1 minus, now we have the final diameter, which we know that is 7.5 millimeters, right? And then we have the original diameter, which is our question mark diameter we're not sure about, right? That's the diameter we're seeking to start our cold working from, our final stage of cold working from. So that's this one here, and that's going to be, these are squared. And then of course there's the 100, just to make sure that your 20 and 100 are both on the same percent ratio. So that's what the thinking is behind this equation process. Of course, this is the variable we're looking for, so they go through the process of solving for, oops, sorry, they go through the process of solving for that variable. Now what they've written here, I don't want you to get your subscripts confused. The final diameter during phase 1 is equal to the initial diameter in phase 2. Let me go ahead and go back to the slide we were looking at before so that you can see what I mean by that. During this process, this is phase 1 and phase 2, right? So this diameter is the final diameter for phase 1, but it's the initial diameter for phase 2. So we'll go back to that. Here you can see what I mean by that. The final diameter of phase 1 is equal to the initial diameter of phase 2 is equal to, then we find 8.39 millimeters. That is the optimal starting diameter to make sure that we cold work our material by 20% exactly before it gets to the final state. Okay. Now you can run that through the process here to find how much cold working that you did in the beginning, but honestly, so this is a stage that's in fact completely unnecessary. I don't even know why they did this calculation. This calculation is completely unnecessary. That you're going to do some cold working that you're going to undo that anyway, right? So who cares? I don't need to know this number. I mean, I might ask you what that number is just to find out, but like practically speaking, you don't need to know it. Then you're going to heat this to restore it back to its original material properties, and then on our second phase, we're actually going to be cold working it again to the final diameter of 7.5 millimeters. And again, that leaves you with tensile strength of 400. That we required a tensile strength of greater than 380, and we required a percent elongation of greater than 15%, and we have succeeded in doing that by going through this two-stage process and knowing exactly where to stop after the this is three-stage, two-phase process, and knowing exactly where to stop after our first phase of cold working. You can also do hot working. It's totally possible to do that process, and I think that happens a lot when. So there you had the possibility of, if you didn't have a 10 millimeter bolt like we had in the previous problem, if you instead shaped it exactly to the 8.4 millimeter bolt and then cold worked it to the 7.5, that is fine too. You can hot work it to that point. There's probably some individual advantages to choosing one method over the other. Like for instance, a lot of the times when you elongate something through cold working, you change the orientation of the grains, and then when you restore it, even though you've restored it in terms of its ductility, you can still have grains a little bit more oriented in one direction. So I mean, there are these very just minute details that could be worked out from field to field about the advantages of hot working versus cold working. Okay, so that's the general idea. Hopefully that helps you with your strategy on cold working. So if you have any questions, please let me know by email, and I'd be happy to help.